Okay, so the setup, hopefully it's familiar. We have two isolated quantum devices. They share an entangled state. And the goal here is we want to provide classical inputs, receive classical outputs, and hopefully certify the presence of a particular entangled state or particular measurement operators. So this is called self-testing. Quickly, we have three regimes of self-testing and increasing level of restriction. So the most powerful is correlation only. We might have a quantum correlation, and this correlation might be only possible to be obtained with a particular state and a particular set of measurements. So in this powerful setting, it's actually possible to certify the presence of any pure state. In terms of measurements, not as much literature has been done. In fact, most of it centers around testing for the presence of Pauli operators or tensors of Pauli operators, although there's some literature on some non-Pauli operators. So the next level, we have Bell inequalities. Instead of just a correlation, we want to look at this sum and have a maximal violation of this inequality using our correlation. And on the right-hand side, we have the classical value. So states here, it's a lot more restricted. Mostly the literature is focused on self-testing EPR states or maximally entangled states. In the case of local dimension 2, we have a lot more. The story for measurements, much the same as correlations, but we're actually most interested in this most restrictive regime of non-local games. So think CHSH or magic square. If you think of it as a Bell inequality, here the coefficients have to be 0 or 1, so binary payoffs. So prior to our results, the literature could only self-test for EPR states, tensors of EPR states or maximally entangled states, and only measurements that were immediately constructed by Paulis. So our results, we introduce an infinite family of non-local games. In the case of n equals 2, we recover CHSH. We're able to show quantum advantage for this entire family, and the classical value is 3/4, so it agrees with CHSH. It's actually a very close generalization of CHSH. What are our self-testing results? Well, we're able to self-test for this state in the case of n equals 3. The details, not too important to digest here, but it's certainly not a maximally entangled state or an EPR state. And the operators we're able to test for are not immediately constructed from Paulis, and we're telling a different story. And the last bit of contribution, we also have a non-example, a non-local game. If you remember Magic Square, think of this glued magic square, and we show that this is not a self-test in the strongest sense. There's really no way to recover much about how the players are winning if they're winning this game. Thank you very much.
Hello, I'm Ungson. I'm going to present new kind of quantum game, which is voting. So this is based on my recent archive summation. And why game is important? Because there are many quantum foundational phenomena that can be described with games, and the complexity classes of games are really important. So as a physicist, I would like to ask, can game compute quantum physics? And I think so. So voting is a game. Voting is a good model of communication complexity classes, and voting is composed of Boolean functions. And there, most importantly, there is a no-go theorem, just like Mermin's magic square. So, yeah, the definition of votings are following. Voters vote on ballots, which is a linear orderings on the alternatives. So actually, voting rule is a circuit, and the circuit can be defined as following. So the key fact is to replace these Boolean functions into quantum functions. Actually, there is various proof, including ultrafilter, hypercontractivity, or category theory, whichever you prefer. But the structure of Arrow's impossibility theorem is that you assume several conditions. There exists always dictator. So I'm going to present a quantum proof using quantum information theory. So this is conditions. So how to do it? I embed the voting into the Hilbert space. Then the superposition is the quantum thing. So then the important thing is that the dictator becomes the perfect cloning machine. So this is voting circuit. I am not interested in what is inside R, but the key fact is the dictator is the cloning machine. So there are three physical properties of quantum voting. First one is due to the no cloning theorem, Arrow's theorem can be proved. And the second thing is, as this is measurement-based quantum scenarios, there exists a contextuality proof using Cauchy-Specker sets or Cauchy-Specker theorem. And also there is Bell-like inequalities. The most simple one is CHSH inequality, but I will not show here. And most importantly, I think using some thermodynamic property of information unit, we can measure, we can explain the infinite error theorem, and yeah, this explains. So I'm extending result. Especially I'm interested in the using quantum voting as a tool to explain Nash's program, which is use the cooperative game to use non-cooperative game. Thank you.
Hello. I'm going to talk about a project which is a joint work with two students, Yijun E and Anna Larnit. Anna is attending the school, by the way. And a few months ago, we started using a proof assistant called Isabelle, which is developed in Cambridge and Munich, to formally certify some quantum algorithms and various results. So we have a library which is freely available on GitHub, which is called Isabelle Maris Dirac. And so far we have formalized the no cloning theorem, the quantum teleportation protocol, Dutch algorithm, its generalization, the Dutch-Jozsa algorithm, the quantum prisoner dilemma, and the quantum Fourier transform. So there is probably enough material now for brave people to formalize more advanced material. And the point is that we found some errors in the literature, so it was not a fruitless experience. For instance, for the formalization of the quantum prisoner's dilemma, we followed the paper, the classic paper, Quantum Games and Quantum Strategies by Eisert, Wilkens, and Levenstein. And in this paper, you have a section on unfair games where Alice can play any strategies, while Bob is restricted to classical strategies only. And they pretend that they give a miracle move that allow Alice to win every time with a large reward against classical Bob. And actually, we found that it doesn't work. We found classical strategies that counter their quantum miracle move. And we tracked the subsequent literature, and we found at least one published paper which reproduce the faulty analysis. So we told the story in a preprint which is available on arXiv. So one question for the experts in quantum game theory, maybe. In the quantization scheme introduced by Eisert, Wilkens, and Levenstein, does a miracle move actually exist? That's it. Thank you. It's not this one. I changed it by another one.
You changed it?
Yes.
Oh. Okay. Maybe we do Vincent next then?
Okay.
Okay.
I see. See your email.
Oh, I'm sorry.
But is mine in order? Can you check this out?
I think so. Did you send me a second version?
No.
Oh, okay.
So how does this work?
Down arrow.
Down?
Yeah.
I see. So hi, I'm Vincent. I don't have so much to tell you, but still I'm here. So the story here starts that we had a dinner on, I think it was Tuesday or so, with Matthias and with Orr. And Orr introduced to us this problem of the quantum min-cut max flow, and indeed he convinced us that it's like an interesting problem. And he asked if we can do something with our restriction degeneration business, which Matthias told you about, to tackle this problem. And indeed we can. So here I present you like the results from the last 2 days. I don't know. So first I explain you what is min-cut max flow. So you have like a directed graph, you have like sources, you have targets, and you have capacities on the edges. And this could look like this. And then you asked for the cut, like you partition it such that the sources are in one half, the targets are in the other half.
And this gives you some kind of capacity, like how much can flow from A to B. And yeah, here, for example, you have like capacity 4 plus 3 plus 2, which is 9. And